You will have to accept.
Okay.
Okay, can you hear me?
Yes.
Yes.
Hear you?
Okay, we have the pleasure to have our colleague Despina Hatzipotiadou from CERN and INFN. She's a researcher at not in Atlas, but in ALICE, another one of the other 4 experiments at LHC. And she's going to talk a little bit about the physics at LHC and the detector, and then she's going to give you a virtual visit underground where the detector is, because as many of you may know, LHC cavern is now open for upgrades till about the next February. So we can visit virtually at least downstairs. Despina, thank you very much for helping us all the times we are asking for. So I give the floor to you.
Okay, thanks a lot, Christina, for the introduction. Hello, everybody. It is my pleasure to be here and show you a little bit of ALICE. But let me first give you a short introduction. So, no, sorry. Zoom. Oh, Zoom. Share. It's okay full screen? Yeah?
Yes.
Okay, so you see this aerial photograph of CERN. The circles are the accelerators. As you must have heard, CERN is the European Laboratory for Particle Physics, located on the border between France and Switzerland. Here, this yellow line is the border. Switzerland is this way, France is this way. This triangle here is the main laboratory of CERN, and the circles represent the accelerators. And we are at ALICE, which is one of the 4 big experiments of the LHC, the Large Hadron Collider, which is the big circle. A double accelerator inside the ring with a circumference 27 kilometers, installed 100 meters below ground. The LHC takes beams from the previous accelerator of CERN, the SPS, the superproton synchrotron, which is this circle. This has a circumference of 7 kilometers approximately. So inside the LHC, the Large Hadron Collider, 2 beams circulating in opposite directions collide at 4 points. And at these 4 points, we have 4 big experiments which study what comes out of the collisions. ATLAS and CMS are the, let's say, the general experiments, which look for the Higgs, for supersymmetry, for any kind of new physics can come out. LHCb is a more specific experiment looking for an asymmetry between matter and antimatter by looking at decays of particles containing big quark. That's why it's called LHCb. And ALICE is the heavy ion experiment. The name stands for a Large Ion Collider Experiment, since our main object of study is the collisions of heavy ions, and more particularly collisions of nuclei of lead. It's a very heavy element. We'll come back to this. Just to say about, we are at point 2 of LHC. LHC has 4 points all around, sorry, 8 points all around, where there are shafts going down, and underground there are installations. The 4 points host the 4 experiments. The other 4 points host the infrastructure of the machine. For instance, point 4, which is somewhere here before CMS, contains the accelerated cavities. 0.6 after CMS is the beam dump. And the other 2 points, 3 and 7, have collimators for the beam. Now, this is just an aerial photograph showing the installations of ALICE. You saw in the previous photograph, you saw that this is the main site of CERN. There is another laboratory also at Prevesen, which was done when the SPS was built. And then, of course, there are installations at all points where there are experiments or other infrastructure, I mean, installations on the surface. So here, these are the installations all on the surface at point 2. And all this is located in France at a distance of 5-6 kilometers from the main site of CERN. In a small town called the Saint-Genis-Pouilly, and actually it is on the border with the next town, which is called the Cergy. And right now I'm in this building where on the front wall, there is a big poster showing the cross-section of the experiment. So I'm in the control room, which is here in this building, and below this white thing here is the shaft and the cavern containing ALICE that you will see soon. So this is a photograph of ALICE. You will see it you will see the real thing. Just to give you an impression of the size, this is 16 meters high, 16 meters wide, and 26 meters long. It is the second experiment in dimensions after Atlas, which is the biggest. And it weighs 10,000 tons. From the point of view of weight, it is second after CMS, which is the heaviest. It contains more iron. So all this is installed 56 meters below ground at the point 2, as we said. And here you see it schematically. The ALICE consists of a central part. It is this octagonal thing, which is a big solenoidal magnet. And inside it, the two beams come from the two sides, collide in the middle. And all around the interaction point, there are detectors with cylindrical geometry, most of them, which see the passage of charged particles so that we can reconstruct their trajectories. They help us identify particles because this is very important for ALICE. And they also measure energy. In addition to this part, there is this separate part here on one side, which is the so-called muon spectrometer. This has a different geometry from the central part. It has the so-called forward geometry, which means that the detectors are slices. So this, the muon spectrometer, which actually has its own magnet also, a big dipole, covers a certain angle for detecting muons. The rest is lost. If you have seen Atlas earlier today, there the geometry is a cylindrical part plus two end caps, so everything can be detected in 4 pi. Here, we don't have exactly this possibility. We have the central part plus the muon spectrometer. So in reality, ALICE is not completely symmetric. So you can consider that all this is a huge camera, which nowadays, after the upgrade that it went through during the shutdown of LHC, has more than 12 billion channels, than 12 billion pixels. And this huge camera with the 15 different sub-detector systems takes photographs of the collisions. Now, where are we? Oh. Now, why heavy ions? If we go back to the Big Bang, which is how we believe our universe started, all matter in the universe was created at the point of the Big Bang. And soon after that, meaning fractions of a second after the Big Bang. So if Big Bang is 0, some fractions of a second, here you see 10 to the minus 10, 10 to the minus 8, what is it? So some fractions of a second after the Big Bang, all matter was in the form of free quarks and gluons, a state that is called quark-gluon plasma. This we can consider as a state of matter in addition to our well-known solid, liquid, and gaseous state. This is the state of the primordial matter, which of course stayed like this very short time because it was like this under conditions of extreme temperature and pressure, which prevailed after the Big Bang. As the universe was expanding, the temperature was becoming lower, the density was becoming lower. So after a point, the quarks became confined inside hadrons, inside protons and neutrons, exchanging gluons to stay there. And they have remained confined ever since. Now, with colliding heavy ions, which travel almost with the speed of light at LHC, we try to reproduce droplets of this state of matter, this quark-gluon plasma, in order to study it, to understand its properties, and to understand how the transition happens from this state of matter to the state that is made of hadrons. Because in reality, this state of matter in the experiment stays around a very short time, 10 to the minus 23 seconds. What we see is the result of its transformation into hadrons once the free quarks and gluons, these which exist free for a very short time, are confined again and give hadrons, particles made of quarks, such as the protons and the neutrons, but also many, many others. Here is a short video showing what happens. You see that the two lead nuclei appear as disks because of relativity, because they, in the axis of, in the direction of motion, the velocity is close to the speed of light. We have contraction of the length, and they appear as disks. So after the collision, you have this fireball created, where in the beginning you have free quarks and gluons, and then as this thing expands, these get confined and they give real particles. And this is what we see with our detectors. So I hope you have some idea now. Just to say that ALICE is an experiment done by a collaboration of approximately 1,900 members from 175 institutes from 39 countries, which you see here on the map. And this is a picture, a photograph. This is what we call an event display of a very central lead-lead collision. I said very central because, as maybe you can imagine, the lead nuclei are big compared to the protons, which LHC collides most of the time. So the way they collide is not always the same. We can have lead ions colliding head-on, in which case the whole nucleus, number one, interacts with the whole nucleus, number two, or we can have peripheral collisions, when they come with a distance of the centers relatively big. So if we have a situation like this, we have a small overlap between the two nuclei, which means that a small part of each nucleus interacts with the other. And in this case, we have less particles produced. But in the very central collisions, we can have up to many thousands of particles produced from one collision. And this is a photograph, let's say, from such a collision. This has been produced after reconstructing the data recorded online. I think this is what I wanted to say as an introduction. I don't know if there are questions at this point, or if we should go ahead with the visit and maybe take questions at the end. Who is, let's say, the moderator, Manolis?
Yes, of course.
So we should go on with the visit, I guess. So let me see.
There is only one comment from Errol Simpson that 2 years ago he had taken 22 of his students to the Alice Tunnel, but I think that according to what he said, they never go to see the detector, but they saw the tunnel and the components. So I think that today it will be nice because he will complete that experience, right?
Okay, so one moment. Okay, this has been muted. Okay, so I'm setting the number. I hope it doesn't get interrupted. I have my film badge, okay. Start video.
I don't know if you, yes, okay, perfect.
You can see it now?
Yes, yes.
Okay. No?
Yes, yes.
Okay. So I will now go out of the control room and
There is a
down.
question. There is a question.
Sorry?
Why lead?
Yes.
Why do you use lead ions rather than any other nuclei?
Why lead ions?
Yeah.
Oh my God, one moment, because they stand around. What's happening?
You use the front camera.
One moment.
Yes, yes.
You have to give me
Yes, yes.
2
please,
minutes because
take your time.
one moment. I'm using a stabilizer arm for the telephone, and this is not behaving properly. So the telephone turned around.
Okay.
Let me see if I can fix it.
Okay.
Why does it turn around? Now it's okay, but will it stay or not? Let's hope that it will stay. So the question, one moment, let me turn it off and on again. The question was why lead ions?
Yes, we have another one. If Alice sometimes produces heavier elements.
Okay, for the first question, why lead ions? Because they are heavy, so we have much bigger mass available at the point of collision than when we have something lighter, for instance, than when we have protons. And we need to have, let's say, a lot of stuff in order to produce this quark gluon plasma. Also, the energy is higher in this way, the total energy, because we use lead nuclei, which means that we strip the atoms of all the electrons, all 82 electrons that the lead atom has, and so we have the total energy is 82 times the energy of the proton beam. Of course, we could have used something else. For instance, in America, at Brookhaven, there is a dedicated heavy ion collider called RHIC, Relativistic Heavy Ion Collider, where the colliding beams are gold nuclei. Gold has Z, atomic number 79, whereas lead has 82. There was another question, but if you can keep it for the end. Can you confirm that you can hear me? Yes.
Yes.
Yes, okay.
Yes.
Okay, so now I'm going to go through the access system of the LHC. You see, this is my personal dosimeter. The access system reads my name and checks that I'm authorized to go down, which I am. And then I have to go through the biometric control, the control of the iris, so that the system verifies that sorry, we cannot confirm your thank you. Okay. The system verifies that the correct person goes in. So now I'm in. You can see on this wall a schematic of the accelerators. And I don't know if you can see, Alice is here at point 2, and one of the beams of LHC enters from the SPS into the LHC ring just before Alice, some hundreds of meters before Alice. So the lift is coming up, and we will go down 51.2 meters below ground. The LHC ring is at an average depth of 100 meters, but in reality, it is not horizontal, it is slightly inclined. And here at point 2, this is the less deep point. Now, while I'm in the lift, it's possible that the sound will be a little bit bad, or maybe it even gets lost.
We might lose the connection for a while.
Oh, your video is stopped? Yeah, hello.
Okay, we're back.
Can you hear me?
Yes, yes, and we can see your
Yes.
screen.
Okay, I don't know why it was lost. So now I am in the lower level, the lowest level, where there are all the installations for cooling. The detectors surrounding the interaction point have on them the electronics that process the electronic signals coming from the detectors and then read them out. So all these would get very hot if we didn't cool them when they are all on. So everything has to be cooled, and here are all these installations. I will now go up some, if you can see some red thing. This is one of the doors of the big magnet, but we'll see it later. I will now go up some flight of stairs and place myself on a platform in front of the big magnet of Alice. That will be at a height of something like 10 meters from the previous level. This is a little bit higher than the middle of Alice. So right now, I'm on this platform, and I'm standing under the shaft from where everything has come down. I guess you can see it. The lights that you see are at the surface.
And we are approaching it.
So, can you hear me?
Yes.
Yes, okay. I'm asking because I can't hear well, because here it is very noisy. There is ventilation the whole time because the cavern is a closed underground area, plus many other machines doing whatever they are doing, so it's noisy. Anyway, what you see here is the big magnet of Alice, and inside it, the beam pipe goes through the axis, and then around it there are the detectors for tracking, for identification, and some calorimeters. This magnet, this red magnet, is a big solenoid. When it is on, because right now it is off, when it is on, the magnetic field is half a Tesla, and this is created by a current of 30,000 amperes. This is a conventional magnet. It's not superconducting like the magnets of LHC or the magnet of Atlas that maybe you heard about earlier. It works at room temperature. And this magnet we have inherited from the previous experiment, which was here in the times of LEP. This is a parenthesis. LEP was the previous accelerator which was installed in the tunnel where LHC is now. That was a large electron-positron collider. It provided electron-positron collisions between 1989 and 2000. And L3 was one of the 4 experiments studying these collisions. So at the end of LEP, L3 left their magnet for Alice, and this recycling kept the cost of Alice a little bit lower with respect to the other experiments. So you see that this magnet has very big doors. Each door weighs 300 tons, and right now they are open because we're in phase of installation and commissioning, but before turning on the magnetic field in order to take first cosmics, and then when LHC starts data with collisions, the doors will have to be closed, and this operation takes some hours because it's done obviously very slowly. If I can, I will later go near the beam pipe where I see some colleagues working, installing some detectors. As you might have heard, for 2 years, this is the third now, LHC has been stopped. This is what is called LS2, Long Shutdown 2. This was in order to upgrade the injectors basically and prepare for the next upgrade of the machine when it would go to the high luminosity LHC. And we, I mean Alice, profited during all this period to upgrade substantially our system. So we have replaced some detectors with new ones. We have modified some, we've done general maintenance and so on. So, well, you can't really see the detectors here, but just if you can imagine, around the beam pipe, there are 7 layers of silicon pixels. That's a detector with 12 billion channels, 12 billion pixels, and this is new. It was installed some months ago, replacing the previous silicon detector that was of a different technology, let's say older technology. Then there is a detector called time projection chamber, which together with ITS provides tracking. These two are the heart of Alice, and they manage to see and tell apart all the thousands of charged particles produced from the collisions. Then on this metal frame that you see, which has 18 positions, 18 trapezoidal holes, there are in each hole 2 super modules of 2 detectors which are destined for particle identification. One is for tracking and at the same time for identifying electrons, and this is called transition radiation detector. And the other is called the time of flight. You might be able to see some blue cables in each of the holes. These are the signal cables from the time of flight. So this detector measures the time it takes for particles to fly from the interaction point to the detection point, with a very, very high precision, 50, 60 picoseconds. And this high precision in the time gives a precise measurement of their velocity. And in this way, we can tell apart protons from charged kaons, charged pions, and so on. And then on the left, if you can see a little bit on this side, there is an electromagnetic calorimeter, which is made of modules, which are sandwiched of lead sheets and scintillating tiles. And this stops electrons, positrons, and photons, and in this way measures their energy. These are just some of the detectors. I won't argue, of course, with more details. The big tubes that you see here are for the ventilation of the inside of ALICE, because when the doors are closed, it's a confined space. And in principle, there is always potentially a certain probability of a leak of gases from the gaseous detector, so there is ventilation continuously. And this structure that you see in front of ALICE, this is what we call a mini frame. This is a big support for all the cables, tubes with cooling water and so on that go inside, what we call the services. So now let me walk to the other side, to the muon spectrometer, so that we get a view also of that. So the muon spectrometer has its own magnet, as you will see, because the magnetic field of the solenoid is contained within all the red iron. So for curving the trajectories of the muons, we have a huge dipole magnet. That's also a warm magnet, cooled with water and operating at room temperature. The field is 0.6 Tesla. And then for the detection of the muons, we have 10 stations with muon chambers. You will see some of them. Just here is another view of these huge doors of the magnet. And now I'm walking in this corridor, which goes parallel to the solenoid. And the spectrometer of the muons is on the other side. Here, you see the tube that brings the water for cooling to the solenoid. So I hope you can see something. The blue thing is the iron of the solenoid. Behind the scaffolding, hopefully you can see one of the poles of the dipole. And then these big panels, these support the gaseous chambers which detect the passage of muons. You see that one has been pulled out. They are on rails, and eventually it will go near the beam pipe. You see 4 such panels here. The other 6 muon stations are inside the magnet, so you can't see them. 2 are inside the dipole and 4 inside the solenoid. This horizontal cylinder between the panels with the muon chambers, this is the beam pipe. The beam pipe itself has just some centimeters diameter, but in this area it is surrounded by material which acts as a filter. It cuts many of the particles going very near the beam pipe in order to protect the immune chambers. And then after the 10th station, there is an iron wall. This blue thing behind the red support is an iron wall 1 meter thick. And this is there to absorb all particles that maybe had managed to reach the wall. But of course, they can't go through it, they are not immune. So whatever goes after this wall, after this filter, for sure is immune of relatively high energy. And the chambers after the wall are the trigger chambers for the immune system. Every system, every experiment in LHC and in general, every experiment has the trigger, which is the system which decides if an event, by event we mean the result of a collision. So if an event is interesting or not. If it is regarded as interesting, and this is based on the information coming from the hardware, the combination of signals, then it is recorded. If it is decided that it is not interested, it is rejected, it is thrown away. So these chambers decide if something was immune in order to record the information from the previous chambers. I just go down so that you have a view of the size of these things. Here, you see they're very big. So next to them, there is a machine that can lift the people, can allow people to work in height. So I'll now try to go near the beam pipe. Just before I go, this door that you see, this red door, leads to the LHC tunnel. Normally, we do not have access there, but you see on the wall, there is the sign that it is an emergency exit. So if there was an alarm and I was where I am now, I would have to force the door open and go inside the tunnel and take the lift that goes up. Otherwise, if I'm on the other side of Alice, I would take the lift that I used to come down here. So now I try to go inside the mini frame near the beam pipe. I hope my colleagues who work there don't mind my presence, so that you see a little bit the heart of Alice. Manoli, can you confirm that you can hear?
Yes, yes, we can.
Yes, okay, fine. It is even possible that there are two groups of people waiting there who will see, because one has to do with the beam pipe itself, there was a missing piece which was installed relatively recently. They have made vacuum, they have baked it, and now they're doing some additional work. And the other thing is some colleagues are installing components of a new detector that is called FIT. This stands for forward interaction, fast interaction trigger, which has replaced some other detectors. And among other things, it's the time reference for the time of flight, this detector. So here I am now on this mini frame. And okay, I will not go nearer. But here are some colleagues I think they're installed, no, this must be the people doing something with the beam pipe. Anyway, you see the beam pipe here. If you read here, it says, beam pipe under vacuum, please do not touch. The vacuum has to be very high because, of course, if there was no high vacuum, we would lose the beam from interactions with the air. And of course, through the experiment, there is only one beam pipe, the one that you see. But through the rest of LHC, there are two beam pipes, one for each beam. But of course, here the beams have to cross each other physically. So there is just one beam pipe. What you see here behind the beam pipe, a kind of a black disc. This is the cover of this detector that I mentioned earlier, the FIT. So what you see here, I don't know if it's clear what it is. This is a compensator magnet for the dipole, because I guess because the dipole on the other side might change a little bit the direction of the beam. There is another magnet here to compensate for that. Okay. I think there are my colleagues working on the FIT. Yes, I see they must have installed some detectors. Anyway, if you see here, the beam pipe goes behind the wall and into the tunnel. So you see here, just get an idea of all these cables. I'm going down. Before I go up, let me just show you, this is the lower part of ALICE, as you can see. So here you have another part of the electromagnetic calorimeter. This combines LED scintillator modules with some crystals which are made of lead tungstate and are inorganic scintillators. So here on this side, we have two types of electromagnetic calorimeters. And last but not least, here, if you can understand what it is, this is the lower part of one of the doors, and there is a hole inside it, a hole rather through it, so that when the magnet doors are closed, but there is no beam in the machine, either because it's a preparation time or because it's a technical stop or something. If we need to do some intervention on the detectors, we can go through that hole and then climb on all these complex things and do our intervention. Of course, if it is something in an area where we have access, because the very inner part of ALICE is very compact. If something, some problem there, repairing it is a big operation which can only be done during a long shutdown. So I'll now take the lift to go up. The lift is quite fast. You can see it coming down, and going up takes 30 seconds. so you can see. You can see here that the lift normally can take 12 people, but according to COVID restrictions, nowadays we can only be maximum 2 persons at a time, since we have to keep the distance. Okay, so I'm back on the surface, and now we'll go back to the control room. So maybe we can take questions now.
There are some questions. We have to
I
let-
tried to answer some.
Okay.
Okay, so let me start sharing the questions. Okay, give me one moment, please. We have, I share one from Facebook first. The question was, what is the flux of the cosmic muons which reach the detector down there, and at which estimated energy?
Sorry, what is the flux of cosmic muons?
The flux of cosmic muons which reach the detector down there, and at which estimated energy?
I don't have numbers for that, but I can tell you that the less energetic muons are cut because of all the material on top, and the more energetic ones are detected. And actually, we can we have seen something like how to say, like an X-ray photograph of the cavern. I mean, there where is the shaft, you can have many more muons, whereas where the experiment is, where on top there is I don't know how many, 40 meters of material, something like that, there you have less because the less energetic ones are cut. But you know, I don't have numbers now in my mind. But maybe it's interesting to mention that exactly because we use muons when commissioning for calibration, for checking the alignment, checking that everything works. And also we do take data with muons when there is no beam, just to make some studies of muons. We have seen some very interesting events with bundles, multi-muon bundles with many hundreds of muons coming simultaneously. This is just a parenthesis.
Okay.
Hello.
The next question, which was also discussed in the chat by Panagiotis, was which are the lowest and highest temperatures that you have seen in Alice? There was a clarification asked if we mean energies by temperatures, but either way.
Well, if we're talking about temperature of the plasma, we measure the temperature of the initial state to be some trillions of degrees, 10 to the 12th degrees, which is some 100, let's say 100 or 200,000 times hotter than the center of the sun. This is at the point of collision in a volume similar to the nuclear volume. So we're talking about Fermi, okay? What was the lowest? By lowest, I don't know what you mean. I mean, this is we measure this temperature of the initial state with many ways. One is by measuring the spectrum of the photons which are emitted as this state cools down, because the photons are not absorbed by the plasma.
Okay, thank you.
Okay.
Let's proceed to the next one. How do you get 30,000 amps without supercooling?
I mean, okay, there are special
Ampere.
generators for this. There are
Excuse me.
special generators for this. The cooling is done with water. I mean, I can't tell you about the technical details of how the cooling is done, but that's how it's done. And actually, all this is quite old, since, as I mentioned earlier, we have inherited the magnet from L3. So this has been there almost 35 years, maybe more, almost 40 years. And once there was an issue with the with the supply of the magnet, but okay, it was solved. Anything else?
Okay, there is another one regarding the magnetic field. Let me tell you. Doesn't ferromagnetic materials exist near the center axis? 0.5 Tesla must create stress.
If there are magnetic materials,
Ferromagnetic materials, yes, near the center axis.
I think we have taken care of using materials which are not affected. I remember, this is as an anecdote. When we were assembling the detector of my group, which is the time of flight, we discovered that some screws were magnetized. So we had to change them all with something that was not affected by the magnetic field. So care has to be taken, of course. And the other thing that the magnet, again, I can remember with problems with my detector, we have these DC-DC converters which supply the low voltage to the electronics, both for the front-end electronics and the electronics for the readout. And some of them had a problem when the magnet was being turned on. It seems that, these were custom made for us, and it seems that something was not fixed properly. So they were moving when the magnet was turned on, and there was some short circuit or something. So we had some trouble in the beginning because of this, but it was solved, okay. Other questions?
Thank you very much. I think that these are all. If I may add one question of my own. So, has quark-gluon plasma been detected with the ALICE experiment?
We have indications.
We have various signatures that indicate that this very hot and dense state of deconfined matter exists for a very short time. If I can give you some examples, one is something called the jet quenching. We do often in high energy collisions, even of protons, two jets are created that go back to back. Jets are, groups of particles, jets of particles in a cone, and we tend to measure the energy of the whole jet. And these tend to be symmetric. Now, in the case of lead collisions, it was found that sometimes there is one jet with high energy and one jet with much lower energy. And it seems that what happens is that as the partons, the constituents of the jet, move through the quark-gluon plasma, they interact and lose energy. So some energy goes undetected, and it depends. If you imagine that you have a small fireball, it depends where the two jets started going in opposite directions. So the one that goes much bigger distance loses more energy, and therefore we see this asymmetry. Then there are other observables that tell us that this quark-gluon plasma is created. For instance, one is something called strangeness enhancement. If you have seen, I don't know if people have seen about the different quarks and so on, in nature, we only have up and down quarks. Then the rest, strange, charm, top, bottom, are created during the collision. So we have seen that particles containing strange quarks are produced in higher abundance than in the case of proton-proton. On the other hand, particles containing charm quark are produced less than in the case of proton-proton. This is called the charm suppression. And this must, for instance, this is seen by studying a particle called J-psi, which is a bound state of charm and anti-charm quarks. And it seems that when this is inside the quark gluon plasma, because of the existence of free charges, what binds the two breaks, and so the J-psi disappears. Well, some of them. Therefore, we see a reduction. So I'm just giving some examples of ways that we see this, that indeed this quark gluon plasma is created.
Thank you very much.
Something else? I see here various questions on the chat, but I don't know, of course, if they...
Most are answered, but let me repeat one of them just for completeness. So is the shielding, the iron wall, enough to protect people near when the experiment is ongoing, or do you evacuate everyone?
When the experiment is ongoing, when there are beams in the machine, there is nobody down there. Everybody is on the surface. That's why the control room is here on the surface. The iron shielding is to close this all. I guess we are talking about the red iron of the magnet. This is to close the magnetic field. This is not to protect from the radiation. The other thing is, I forgot to say when I was down there, the shaft from where all the things have come down, which is now open, before LHC starts, will be closed. At the level of, let's say, of what corresponds to the ceiling of the cavern, long concrete beams will be added so that it is closed and the radiation does not go out.
Thank you very much. We don't hear you.
Can you hear me now?
Yes, now, yes.
Okay.
Okay. So I think that these are all the questions that we have. We have many thanks from people also from Facebook who say that they hope to be there someday.
We also hope so. We also hope that we can welcome visitors. I don't know exactly what will happen. The only information that we have at the moment is that the CERN, which is in orange now, will go to yellow next week, which means that the rules, the restrictions will be different. So I don't know. For the moment, outside people cannot come to CERN. Maybe when it is yellow, they can. And then eventually it will go to green, I hope. But
we hope so too.
These things are normally indicated on the CERN page concerning visits and so on. And we have also our own page about visits. So I'm sure if you look on the web, you can find them.
So are there any other questions?
I would like to make a comment, except from thanking Despina for helping us, just to let people know that last Monday, Atlas has lowered down from the shaft a piece of equipment, 112 tons. And everything was documented in a YouTube movie that will be shown tomorrow at 5 set time. I will put the link on the chat.
Okay.
Thank you very much.
So you've installed one small wheel and the other will be for when?
It's getting ready. We
Okay,
hope it will be installed before closing up.
okay, very good. So then we can start.
I don't like one and an old one. It's very asymmetric, but we will see.
Okay.
Okay, so if we don't have any other questions, on behalf of everyone, I would like to thank you very much, Professor Hatzifotiadou, for this excellent tour. And we hope to see you again and be there and to do this tour face to face.
I also thank everybody for the attention, and I hope that you are able to come and see everything in person sometime soon.
Thank you.
Okay, so
Thank you.
Bye-bye
Thank you. Thank you.
bye-bye.
Bye-bye.